but we are using this room. So let's see if this room is good for us. First, some admin stuff would be like, so please register your group so that we know how to, the time management on the second last class, right? You do the presentation in class. So that would be something we ask you to do. I mean, if you form the group, please fill it in, because some people may not be able to find their group mate. Then they may ask you to see if they join your group, but otherwise we allow 1 to 6 each group. So if you really want, you can do a one-person group, but it's not really recommended. I recommend at least 4 people would be the most appropriate, but you can form as large or as small as you want, because some people really want to be on their own. So you present the class, so each person would get, no matter the size of the group, you get an equal number of minutes, so it will be fair. So everyone's supposed to present. Okay? So now let me get back to the slides. I guess last time we stopped somewhere in the almost at the end of 5, right? We run the we consider the at the end we consider that is how to interact, right? That's where we stop. Okay, so but since multiple regression is a very important topic, let me quickly review what we have done. Okay, so to give some idea again. Okay, so in lesson 5 we consider the regression, right? And very quickly, I mean, I'm not going to go into a lot of detail. Would be we talk about how to construct confidence interval, right? Because the regression, what it gives you is the point estimate, right? So you want to have interval estimate as well. You have the interval estimate coefficient and interval estimate for the predicted value, and also we have hypothesis testing. So that would be the goal. Okay, and the next thing we have is to look at the case where we allow more than a variable, which is topic 10, we call multiple regression. And you do notice that probably you would do is this is the one of the most important subject in our class, right? Is to run regression, and this will be reflected in your assignment, right? The assignment 2, which I'm still making. I mean, I made half of them last night, so I will make the other one tonight as well. But that would be asking you to work on bin scatter plot, and also the Lewis and the regression, and that would be the goal of the assignment 2. It will be very similar to assignment 1. Asking you to do some Python code that you would add that from the PPT, which we have discussed. But this time we give less detailed instruction, give you more freedom to play around. Okay, but there was still some instruction there, but hopefully it'll be more fun. So the multiple regression would be the case where you basically fit in a plane, right? That minimize the vertical distance. Okay, and we know that to run the regression, that would be, right, the simplest is the formula API, right? That would allow us to, if you call it data, you can specify the formula directly. So you don't actually do with the matrix. That is convenient for if you do multiple regression, because you want to try different types of stuff, then you don't want to change the matrix, right? So the easiest to do is using the formula way. So the star glazer would be the package that we said that would enable us to produce a report nicely, right? In particular, you look at the R squared and adjust R squared is the way to see how it fits, right? If your concern is how fit the model is, right? Of course, when you say the fit the model is, you would also look at whether the coefficient have stars, right? Hence the name star glazer, right? You would expect at least to have 2 stars, right? The worst case 1 star. If no star, then probably that's not too much useful, right? And that is the result of hypothesis testing. And some of you may ask, what are the last 2 items there, right? Residual standard error will be is basically MSE, right? So the way to measure is how variation is it, and if this is smaller, then it's of course it's better. And F test is related to T test we have. Usually you pass. I mean, there will be. I'm not aware. I mean, any real-world regression, you don't pass this guy, right? So F test is testing whether all the coefficients are 0 or not simultaneously. So usually you will pass. So usually you don't need to really worry about that part. Look at the T, and then that will be sufficient, right? Because very unusual case, you have F test fail. So it shouldn't be an issue for us. And we run this regression, right, and see this is the last time we stop here, right? We have age and, right, we somewhat stop age and gender, right? We stop at this one, I guess. Did we? Let's see. Did we stop at this one? Yes, we have intersect that one. And also we do the square as well, right? So we have done the square part. And so this part is done, right? This nonlinear thing, we actually did that, right? That's how we did, right? And also we allow interaction. That is the equation we have, right? We allow the wage will be different by gender, also by age, but also age and would work differently for men and women can be. So they allow interaction term. Okay. So that will be a question. Okay, the last one we want to talk about is this R square. Okay. That will be the same as we have said. R square is how much is the thing we explain. In particular, this form is more desirable because this is something later you will see when we talk about other R square measure. So basically, it's 1 minus, okay? And the SST is the thing we want to explain, right? And SST is something we didn't explain yet, right? And if you change it to R adjust, will be in this formula, and probably ask why we use this one when we compare models. The reason is being that if you increase more regressor, as we said, it never decreases because you have more thing, then at the worst case, it doesn't change, right? Because you are minimizing SSE, right? Remember, the goal of what you're doing, right? Regression is to find the coefficient that minimizes SSE, right? So that means that if you add one more nonsense, at most the coefficient becomes 0, right? So it can't be worse off. So that means that if you want to compare different regression, whether say you want to add a square or for h, right? Whether you end up cubic, so when should we stop the polynomial, right? Then you have to decide how many coefficients you want to estimate, and that is the parameter k here, right? And if you have a much larger system, more complex system, k will be larger, right? As k will be larger, this is negative, right? So the denominator is smaller, and this is smaller, this is bigger, right? This whole thing is bigger, that means the R adjust will go down, right? If you add something that does not reduce the SSE, then it's not that good at, right? Just don't add it if you don't explain more, right? So that is why we have adjust R square. I mean, if you see the output, right, is here, right? Adjusted R square, okay? And that would tell us when you will stop, right? Because that is if you care about prediction, right? So if you want to compare different model, you decide how many square you want to add, right? Square term, how interaction term to add. The easiest way to look at is to just R square to see which one would be the best. Okay, we'll talk about this more by the end of this class. Okay. Now lastly, beside R square, okay, sometimes we actually want to plot the one that also look at the feet. It's called the y hat plot. Okay. So so basically, maybe it should be y hat y plot, but depends on how you like. Okay. And that is maybe a look at the diagram to show you what is going on there before. Maybe show the example here. Okay. Then you will see what's going on there. So suppose I want to do this. Okay. I look at the price, and then try to explain by distance and rating. Okay. And why? Because maybe you want to book a hotel, then what you want is to care about how far away from the city center and how good the hotel is, right? The hotel, how good it is, depends on how the other customer rated, right? That would be something you think that would be most important thing. Of course, you can add more, but to illustrate the point, we just use the two. Okay. Then how to run this regression? Maybe let's run it together again because I hope that we can start with something that more fun. Okay. With data here, right? And Dan know it. Okay. I don't think we have to explain this part very well. You have done this in your assignment 1. Something similar. I asked you to do again in assignment 2 as well. The first question, down data, I do combination, but that would be part of the thing. Okay. And second would be, I want to look at the filtering, right? This is very important to filter data to figure out the things you like because you start with the raw data. So always do the filtering, pick up the observations that you need. That is something we do in the second round. Okay. So this is what we do. I hope you know what's going on because we have done this many times. If you have done the assignment, then you will know there's nothing new here. Okay. And in deep population, we don't need to ignore this guy. It depends on what you want to do, right? Maybe you are focusing on not expensive hotel, that may be okay, right? Or you can remove this restriction. This one doesn't really matter that much, but I just copy. So this is the regression we need. Price, distance, rating. Okay. So that would be the idea. Okay. So that was the regression. Of course, we can look at the summary first before we continue. So let's forget about this guy. Let me look at print the regression summary. I haven't loaded the package, so I need to go back and pick up the package. Should be this SMF here. So let's see when this regression. Okay, first thing you look at. Okay, R square is okay, right, from top to bottom. I don't know whether you can see from the back. That explains 27%, so it's okay. It's not high or low, right? Because R square doesn't really say anything. It's only useful for compare, right? Then maybe if you want to compare, you want to consider something like distance square, right? Maybe if you want, you can call regression 1, right? And I create another one, df, say distance square will be equal to df distance and raised to the power 2, right? And I want to fit the other regression regression 2, I have distance square. Maybe I move this to the down so you can see what's going on here. Okay, and I can run print regression 2 summary. Okay, and if I run this one will from 27 to 35, and just R square also increase. So I guess that is a better model if you want to use. Okay, if you just based on the fit. Okay, R square or R square adjust. I mean that's a substantial increase, so I will probably use this one. Okay, this is the model, right? Then the thing is, look at the intercept means almost nothing, right? Very interestingly, usually expect the intercept would be something, but turn out this, right? The coefficient is almost like 0. Okay, and the rating actually cares a lot, right? And distance square is the coefficient is okay. Okay, so that would be the things we look at. Okay, and now now what we want is to go back to here, right, and fit the y hat y table, y hat y, right? So what we want is to see how fit they are, right? So maybe we just try to do that here. Okay, this y is the original data. Y hat is the one that we do regression. Maybe we do 1. I mean, or we can do 2 as well, but or maybe 2 to make sure they're slightly different from your slide, right? So have more fun. So that would be the 2 number we have, and what we want is to have plot a scatter plot of this, and then draw a line. Okay, that's a y hat y. That's very simple. So here is I have matplotlib py plot. Okay, probably you know very well from the assignment 1. And the first line is just I just plot the case I want to put the line 45-degree line, right? So that means that I need to tell what is a line number there, right? So what the x and y. So just I put a line that will be minimum, the maximum, the y hat, because you see y hat is the x-axis, just the odd x-axis there. And I have linear space, means I cut each 100 point, data point. And I draw a scatter plot and the size of 10. And this is the thing I have. So let's copy this and run it. Okay. So this is the line. Okay. And you will see the 45-degree line here. So maybe it's too big here. So why we have y hat or y hat graph here? Why we have the predict here? Because we want to look at, remember the goal of this exercise. We have done so many, but remember the original question is, we do so many things is to find the best deal, right? You want to go to a trip, then we want to find the best hotel, right? So what is here is, according to the data, if you look at the distance and rating, right? The price is supposed to be like $80, I suppose, at this point. $80 is here, right? Just use the pen, right? It's here, supposed to be. Suppose I look at this using the orange, right? Suppose here. I look at this particular set. From the data, it tells us this combination of distance and the rating is supposed to worth $80. Okay? And in general, the hotel should be here, right? So everything that's above that is overpriced, right? In terms of distance and rating, right? Maybe they're good at other things, but I don't care, right? For me, I just care about distance and rating. And they may actually maybe charge more for no reason, or because they have nice spa or nice view, which I care nothing, right? In that case, that I don't want to overpay for that, right? And the best deal will be this particular guy, right? So if I want to look at the best deal, that will be somewhat here, right? All these are, the purple one are the good hotel in terms of the pricing, right? Which one to pick, another issue. There are some criteria you do, but at least if you run the regression, right, you put in whatever thing you think you care, right? That's not R square related, right? To put the thing you care, right? Then you just run this and look at this one. That would be the things that you like, right? Of course, if you care about how fit the model is, right? If the model is nice, then everything should more or less follow the red line, right? If it's far away from the red line, then your regression is not that good. So that's how the two use of this graph, right? First, you look at how good the fit your regression is, right? Suppose if your model is perfect, everything should be on the red line, right? The more dispersed the data around the red line, then it's worse. And also you can see how well the data is, right? If the model works very, very well between this region, if the further away, right, it's not very good, right? So that means that, I mean, you will be more cautious if that's far away, right? So the regression can be maybe sometime work very well for some region, then you have some confidence over that range, okay? So because I have a linear model, it may fit particular region better than others, right? So, I mean, that is used as, I mean, confidence interval also tell you that as well, right? If you remember, but that would be the key, okay? Is that okay? I think we now cover almost everything about regression, okay? That you will be able to do the assignment after I do it. I finish it tonight. I mean, the TA will take a look whether I make the assignment correct or not, and probably will release a few days later, okay? That will be probably up to this point, I guess. So is there any question before we proceed? Because I think the regression is the single most important thing you want to get out from this class. So that's why the assignment 2 will be the focus of that one. Okay, ask you to do a different regression and how to look at the graph and do it in Python, right? I guess using the IT tool is the most important because you may learn how to run regression using Stata or eViews or whatever thing, but since we're IT manager, then you should know how to use Python, okay, to do the job, okay? Okay, is there any question? If no, then we go to the other chapter. I think we're done with this chapter there. This is a YY part, okay? Is there any question? I mean, if you have any question you don't want to ask, you can ask in the U reply during the break, but if no, then we'll go to the second set of slides. So let me go to lesson 6. So as we said, we're slightly behind the schedule, but so that's why I only covered chapter 11 very quickly. Chapter 12 I will skip. For time series regression, I think it's okay if we don't cover it because even the cover it just where we just sketch the surface a little bit because if you probably notice, if you really want time series analysis, it will be, even for undergrad, it will be a whole semester class. And then for you, I guess, only you doing financial data, you will need that. And I guess most of your IT managers, so not going to be doing financial data. So I don't think we actually need them. But if you look at it, it's not too much different from the regression. Just you fit another model, just using another command, and that's it. So, and to be honest, if you don't do financial data, you actually don't really need them that much, unless you're doing high frequency data. If you do daily data, usually that doesn't really matter. Okay, so I hope that gives you some comfort that we skip that part. Okay. So the first one is modern probability. Okay. So there are many things in regression can be done. Okay. For example, why? Okay, the thing we want to predict. We don't put any restriction, right? Can be any number, right? But sometimes the data set only have some limitation, right? So say, for example, y can be only 0, 1, right? What is y 0, 1 is the case where you ask people whether they like spicy food, yes or no, right? Or whether they like a particular rock star, yes or no, right? So these are the questions that, or they like your product or not, yes or no, or they click the button on the website, yes or no, right? You want to have that model, right? Because you want to predict what the customer do, right? Or in general, the number can be just a non-negative, right? 0, 1, 2, 3, 4, 5, right? How many times they click, right? Then your regression will be very different. I mean, in general, there are many ways to handle that because when you have a y is limited, we call limited dependent variable, the way to do regression will be different because there are many other techniques that you can do because of time. Then we will, although the textbook, we only focus on the case only 0 or 1, the y. Okay? Of course, we can still apply regression model, but we want to tell you there are other two ways that we call Probit and Logit that will be very often we use it because why we talk about that, because later when you learn machine learning there will be some way to do that as well. So of course that's why we cover that, but we just very briefly. Okay. So for very briefly then that will not be emphasis for your assignment, for your test, but I just want to cover it as quickly as possible to give you some idea what's going on. But that part will be so it's still crucial, right? So, but I try to cover as much as possible. So very often we do binary data. I mean, if you learn undergraduate statistics, you also focus on binary data as well, right? Yes, no question. The proportion, right? And often we model that y as a continuous variable, as a probability that you get y, or proportion you get y, right? That's your undergraduate, like you just draw a random guy, how likely is that guy is 1, right? That's proportion, right? So, and proportion, we want to explain how it depends on x, right? So how likely that someone do something, okay? So that would be the goal, okay? And of course, nothing can stop our regression, right? Regression can do anything. So that's why we spend so much time on regression. We can do regression, right? Explain the probability having 1 by a linear thing, right? Say whether you like spicy food, right? The probability that spicy food depends on how old you are, right? Maybe x1, maybe how far away from Sichuan, right? Is the estimate, right? So that would be the way to estimate, okay? The only problem is interpretation. When you have linear model like this, there's no limitation on your model can go beyond 1 or go below 0, right? So we model predict the probability is 1.5. What does that say? Can we say something? Or the probability is -5. What does that say? Of course, you can say, okay, that's fine. Just like the bigger, the more possible or less possible, right? But still, is it not very clear what it means? But you're still okay. I mean, you would say probably -5 is less likely than the model that say probability -3. Maybe probability 2 is better than probability 1. But I mean, yeah, it's okay. But I mean, we're just stretch ourselves a little bit. But anyway, so let's see this example, okay? And this one is asking a case study, which I'm not going to run the Python code with you because of time, so I just go quickly on this case. This case is studying whether if you smoke, okay, and whether you will get worse, right? The health, that is very important, right? In the old days, right? So, I mean, of course, you are young. You don't consider, you will not see the change in the health, right? So that's why the study will focus on whether 50 to 60 years old people who are health might be declining. Okay? And ask them 4 years later how good they are. Okay? So it's a very long period of study. So, well, if they remain healthy, that's 1. Not so healthy, that's 0. The 0-1 question, right? Are you healthy? That's it. Okay? They ask it before and after. And data from Europe, look at 14 European countries, and then from 2011 to 2015. And if healthy means they feel good, okay? And the N is like 3,000, okay? And of course, the easiest look at this one, right? Whether smoking actually change, right? This is the most stupid and basic one, right? This is just simple regression, right? Simple regression just, right? And do note that healthy or not, it's just 0-1 in the data. Whether you smoke or not smoke, it's just 0-1, right? You're smoker or not smoker, right? There's no half smoker, right? There's no, you smoke half a cigarette, it's still a smoker, right? It can't be half smoke. So look at the scatter plot like this, okay? The data is featured in this way. So the size of the circle represents how many people there are, right? So this dot means that this much of people actually is not smoker and do not remain healthy. And majority of people actually are non-smoker and healthy. And look at the smoker. Some people are not so healthy and some people remain healthy. You look at the graph, naturally we expect this downward sloping. If upward sloping, then you smoke more, right? But of course, you will likely downward sloping. And the slope is like 0.7, right? So that means that when the regression, you will say 7% if you smoke. After 4 years, you become less healthy, right? So maybe say out of 100 people, right? By luck, if you smoke, then 7% more people you will be less likely to be healthy. So this is the number. So this number, I don't know that is high or low, right? And the problem is you have to control many other things, right? So there are two, from economics, or from common sense, you can think the two things, right? One is smoker may be people may be poor, right? They don't have other entertainment, they smoke. Or they work very hard, they need smoke to make them awake, just like coffee, right? So then actually if those people are poor, they're less likely to be healthy, okay? If you control the thing. But also can be say, okay, only if they can smoke, if they have money to afford, right? So maybe only rich people can smoke, right? Poor people can't. Or people actually smoke with drink or whatever, who knows, right? Or if they don't smoke, they do some other more crazy thing, right? They may, in Europe, maybe they have taking some drugs, right? Or drink more beer, who knows what, right? So it's unclear if you don't control other things, right? You don't really know, you miss many things, right? So is it going to be bigger and smaller? So that's a question, okay? So how do they do it? Look at the example they do is look at adding other things as well. So say look at this one interesting is look at education, okay? Without thinking about whether they are smoker, right? Because we want to see whether other things remain the same. Because remember they look at the case different between after 4 years, right? And they see education, okay? You will see actually people study more, okay? Actually, health goes down. Why? One possible reason is people actually don't have study. They work labor job that they make them healthier, right? But when they study more, right, go to the college, which is here, right, 16 years, right, 6 plus 6 plus 4, right, 12 years, and right, I think this is including kindergarten. So probably this up to the this high school, I guess. High school. I think if they start the kindergarten right here, and this is going to be before the college, they still increase because I think people in the white collar and actually stay in the office, right, more healthier, right? And when they go to the master, then also the healthiest, okay, that like you, okay? If you go to Ph.D. like me, okay, then the healthy will go down. So if you just care about your health, probably should stop here. No more master. I mean, if you do one more master, then probably there's a problem, right? Your health goes down. So probably this is the best time to stop, right? If you do one more master or whatever, that will go down. Income as expected, right? Richer people actually more healthier. There's no uniform goes up. And this is the regression. Okay? And let's highlight several main points here. You can see now the coefficient is getting less. Okay? So actually smoking is not as bad, but smoking, because 7% now is 6%. Okay? So one thing you do notice is, okay, a good education is actually up to college degree or master level is actually make you healthier. That's good. So now you're okay. But if you consider taking one more master, then probably is no, right? But it's good that there's no star. So I'm okay. I mean, not that bad. I mean, as I did my PhD, is okay. But what does that tell us is you should exercise regularly, right? So you have 5% more, right? So it's something like if you smoke but you exercise, then seems to be cancelled out, right? And if your income is high, then you're also better. And your BMI is low, that's good, right? So you exercise and actually will have low BMI, and right? So it seems like you can see if you're exercising regularly, if you smoke, actually cancel out. Okay? That means that by not smoking, you are doing exercise, right? In some sense, right? And unfortunately, in this model, female has no difference. Usually, you will see female is more likely to be healthier, but probably 50-something has no bigger difference there. And you can see ever smoke actually has no impact as well. So if you smoke like very young, but you quit smoking, that actually is not a big issue there. But anyway, this only 3,000 data from Europe may not be applied to China, right? Chinese may be different from the rest of the world, right? Because we eat many different elements from the element table, so it would be, we are immune to many things anyway already. So this interval, so I mean you look at confidence interval, they turn out to be 1% or 11%, right? So in the worst case scenario, if you smoke, your health will decline by 10%, right? But the best case can be just 1%, so it may not be that bad. Okay, so as we have said already, all the interpretation already. Okay, so here comes the problem of this kind of model. It's because of when you do the prediction of the data. In general, the data is between 0 to 1, but there's something is 1.01, then what does that mean? Of course, no idea, okay? Of course, you use the model, not for prediction, right? Maybe 1.10, you just tell people just 1, right? You'll be more healthy anyway, right? But it's not clear what do we do. So that's why there are other reasons that is a problem. So that means that instead of using the linear model, we use non-linear model. Okay, and the non-linear model, there are two ways to handle. One is called Logit, one is called normal. Okay, but their interpretation is a little bit more difficult. Then in this case, we'll keep them between 0 to 1. Okay? Let me quickly mention what it is, then before go to break, maybe allow me 5 minutes, then we'll break. So if you remember, regression is what? Regression is like this, right? You have some data point here, right? X and Y, right? And what we want is to find the line, maybe other color, right? That best fit this data, right? Of course, X can be multidimensional, but that is the regression idea. But the problem is it can go beyond 0 to 1, right? So your prediction, right, depends on where your X is, right? Can actually, this may be the number here is 1. This is 0, right? If you give me this X, can be beyond 1, right? And if you give me something very small, then it can be negative. It can be lower than 0. That's an issue. So how do we solve this problem, right? Because in this model, right, we have YP probability, right? YP, right, is alpha plus beta X, right? So how do we solve the problem of getting non-zero, right? Less than 0 or 1. So it's to find something that always gives us 0 to 1, no matter what. Okay? And luckily, actually, in probability, we have something like this. Okay? I hope you still recall what you learned from the college. So let's start with the normal thing first. Right? Something you know normal is a bell curve, right? I hope you still remember that. That would be something like this. Normal with bell, mean, mu, this, right? And the mu decides the location, and sigma is how spread they are. That you learn in the undergrad, right? The bell curve. And the shape of this bell, right, is we call density function, small f, right? And the density function, right, tell us that suppose if I look at this area under the curve f, right, suppose this is called A, right, then this will be the probability that x less than or equal to A, right, will be given by this area, right? That's what you learn in the high school, sorry, in the college, right, the first year stat. And if you look at this area and the relationship between this number and the area, what you have is this guy, right? It's called the big F, CDF, cumulative function, right? If mu is here, you something like this. At most is 1, the bottom is 0, right? You learned that before, I hope, right? So this is the CDF, right? If this area, the size is called, say, B, right? If A here, you go up here, this is B, right? That is something, hopefully, you still remember a little bit, okay? So that is how we will use this function, right? So you just tell me which x you give me, right? No matter negative or positive. I go up here, then that is my model. Okay? My model is, you give me this, f alpha plus beta of x, okay? So I give me the x, I transform it, right? Move it around, and I go up, look at number, that is my probability, right? Doesn't matter because remember if you learn from the undergrad, right? You multiply something plus something, it's still a bell. So the same shape, right? So the way to estimate this kind of model is to figure out what is the alpha and beta. You change the shape, right? So such that to fit the model the best. Okay, we will talk about the maximum likely estimate later, but that is the model we're doing, right? Instead of fitting a line, we just change mu and sigma, right? Changing the mu sigma will move this guy, move this area back and forth, right? Different mu will be, this is the where it goes up, the most steep. So you just keep moving and more sigma, more spread out or something like that. So that will be the goal. I'm just mapping the Probit. Probit is the normal, okay? Logit is the logistic. It also looks very like the same, the bell curve. So basically, we are fitting the bell curve to this one. Of course, you ask, do we have to fit the bell curve? Can we fit any other curve? Yes, you can fit anything, as long as you figure out the distribution function. You can just fit it. That's no problem. Okay. But the most useful one is the Probit and Logit, because why Logit is you can do closed form solution. You can do math. If you don't, but very often they're very similar to the model that was normal, the bell curve. Okay. So then what we have is, you give me the x, I multiply by alpha plus beta x, move around, and go up. This is my probability. Then in this case, I always have 0 to 1. Okay? I mean, of course, I'm not requiring you to fully understand this, because this is, if you understand this, it actually can be one semester class to look at this limited dependent variable at the graduate level. But I just want to review what is there, because what I want to say at the end, you run a Python code anyway, right? Which basically, if you look at the Python code, what we will do, we just change from OLS to Logit, and that's it. That's done, right? So in terms of math, that is very simple. In terms of Python, it's very simple. With the Logit there, if you run a Probit, then it will be somewhat like here, right? And we'll give you more detail after the break. Don't worry. But I hope I give you an idea why not fitting a line. But we can make sure that it's from 0 to 1. Okay. So let's have a break of 15 minutes. I'm sorry I took longer than usual, but we'll break. We'll resume at 10:40. You still have a full 15 minutes break. In the meantime, I will answer any question you might have. Okay. Now let's see how your response you are. Wait. See if 35 of you respond. See if I can say more. So the idea is following. So the question is, don't understand what's fx, this thing. So let me go again about the data. Okay. This x, this is y. Okay. The data you have is different from before. Is you have either y is either 0 or 1, right? So you can imagine the following. The data look like this. Okay. Maybe x is low, y is like this, right? And when x is high, something like this happen, right? If you do a normal regression, what you do is you will find a line, right? The line represented by ax plus b, right? To fit this guy, right? Find the best line, then you're done, right? You're done. That's called LPM, right? Linear probability model. That's what you have, right? You will find the distance from the black dot to the red vertical. Some of them minimize the SSE, right? Sum of squared vertical distance. Okay? So now because we want to, just to remind, this is 1, right? The height here is 1. 1 is here, right? This is 0, right? Of course, the problem, as we said, right? If your data like here, then you map, the model will tell you it's 1 point something, your data is here. It will tell you negative probability, not very desirable, okay? So what you're going to do is trying to fit, instead of a line, fit non-linear line. That must be from 0 to 1, okay? The line that we're trying to fit is like the following, okay? The one to fit is to fit the f function. By f function, if the bell curve is called f, right? Or if you like calculus, this df is just f. You differentiate that with respect to x is the f, right? The density function. So if you change the bell curve, what you do is, this is the bell curve, right? So look at the area up to here, right? Then you can change it to something like this. A curve that is from negative is 0, positive is 1, it's just like this. It's always from 0 to 1. It's always increasing. That's called big F function, the length function in the textbook, right? So if logistic, there will be ex over 1 minus e to the power x is 1 over 1 plus ex, right? You can check that out, right? And in that case, this is the model, and that means that what we are doing, say, Probit will be just trying to see to fit this kind of thing. Okay, the blue one. Okay, and of course, because it's a normal, right? Normal is represented by the mu and sigma, right? If you change different mu, say suppose you decrease the mu, then you will have something like this. The same thing, but you go up earlier. Okay? And if you change sigma, then you will be fatter. Like, if suppose the purple one is a sigma, you increase the sigma, then something like this happen. Okay? So then it depends on the mu and sigma. Change that thing, you will fit it. Right? That's how you fit the thing. Okay? And that is pretty much how we do. Right? And also, beside this, we don't look at how to fit this guy. Right? We actually do another transformation allow you to combine this, right, with coefficient A and B, right? Because this is, you do 1x, right? If you x, y, and see how you map it, right? You have to convert all the coefficient into one number, right? And you map to here, right? Because suppose you have, say, x1, x2, right? So you will be beta 0 plus beta 1 x plus beta 2, say x1, x2, and up to xn, right? So basically you would change this to here, right? You figure out, you combine everything, and then try to figure that out. All right? So that is the main idea. I mean, there's some way to measure how the fit the model is, but that's pretty much the way we are using. All right? So that is that clear? Because we'll keep. That's why later you will see we will call the maximum likely estimate, because we have to figure out this mu and sigma, and then we have to estimate this beta 0, beta 1, beta 2, okay? And for us, it doesn't really matter, right? Because we want to do prediction, right? We don't really care about the black box, how they estimate, right? But that is what, I mean, try to convince you that it's something that we are doing in the background. I hope kind of answers the question. F is just the cumulative CDF, right? But you don't want to directly use this, but you use the linear transformation of this. So we have more freedom, right? Because when you have more than one dimension, then you combine them, right? You X, Y, Z, right? You have X1, X2, X3, we do linear combination, and everything will map to there. Is that okay? Not sure if you still not sure, ask me again in the second break. Okay? I try to see if I can come up with a more intuitive answer for that. Okay? So far so good. Yep. Only one people think we are in first day. So yeah, sunny day, but I think typhoon signal number 1 is on. The speed is okay. Most of you can follow. So what is, yeah, okay? Oh, remind me of him, okay. Look like him, okay, that's good. I look that young. Fear is the path to the dark side. Yeah, there's nothing to fear, I guess. So I think it's okay, and then let me know if you have any question or problem. We try to figure that out, okay? So just to quickly go over this one, because as I said, this is not the focus of our class. So I just quickly go over the only difference is the Logit, okay? And we'll also use the stat API as we do regression, right? So not going to talk about that, but the main thing is this interpretation, okay? And here you see this model is crappy because all the p-value are larger than 0.5, so 0.05 they're basically not useful because I have a crappy model to start with. But the thing is, I want to draw your attention on one thing is called pseudo R square, which I will define later, okay? The pseudo R square, as you can see, pseudo is a fake or something very similar but not the same, okay? And this pseudo R square is asking how fit the model is. So even this crappy model, not like this model, the the Logit actually gives you 30% of fit. Okay? And the R square again is bigger the better. Okay? And I will explain what the pseudo R square there, but it's very similar to R square. But that would be the thing. Okay? So I will define it very soon. Okay? And the point is, one thing I want to know is the marginal effect. What's marginal effect is how x changes by 1, how much y changes, right? But you can see it is highly nonlinear. That's a problem, right? Because if you recall what we have been doing in the regression, if you have simple regression, y equal to alpha plus beta x, right? If you do calculus, dy dx is beta, right? So it means that if you change x by 1, y will be changed by beta, right? That's clear, no problem. And if you have this, you set the color, y equal to alpha plus beta x plus gamma x squared, your square term, what is the marginal effect of x, right? That also, probably you know, so we'll know very well by calculus, right? Will be dy dx would be beta plus 2 gamma x, right? So it's not very straightforward because of the slope depends on where x is, right? So the marginal effect is the x is bigger, the marginal effect will change, right? Bigger usually, if gamma is positive, they will be bigger, right? So then usually how you would evaluate this guy is evaluate at the mean. So usually you would say the marginal effect at the mean, right? You replace this guy, right? So you evaluate at mean. Right? So that is something usually we report, right? Because on average, at the average level of x, if you increase average x by 1, that's how much y will increase, right? That is the interpretation of this marginal effect. And you want to apply it to this nonlinear probability logic as well, right? Of course, the computer will do differentiation for you, okay? And you do all the crazy math, and that is the Python with the following, okay? We call the get marginal effect at mean, okay? And if you print the marginal effect, right, it will give you, if dy dx, right? So if you increase x2 by 1, the probability will increase by 49%, and if you increase x1 by 1, they will increase 16%, right? So that would be the idea that behind that, right? Because when you estimate Probit, the coefficient by itself has no particular meaning, right? Just like when we run the coefficient of square term, what does that mean? Right? It's not very clear. You usually want to care about the marginal effect. Right? Same idea. Okay? So the Probit is the same, just the Probit change the Probit. Okay? Before you log it, you do the Probit. Okay? And you can also get the marginal result, so on and so forth. So this is what I said, right? If you have just seen that, right? The index, linear index is the alpha plus beta x, right? Linear is like this way, and the one I mentioned is the probability logic looks like this curve, right? So that means that if you're looking at usually look at the mean marginal effect, okay? Probit Logit linear probability model give the same result, no difference. Okay? But when you are away from that to more extreme value, then probability logic will be better, right? So if you care about the average thing for your prediction, that's no problem. But when the model is more extreme, right, then you want to use Probit Logit, right? Because Probit Logit will give you negative probability of probably more than 1, right? But Probit Logit will be loyal to that will be given. So really, it depends on data, how diverse the data you are. Your data very spread out, use Probit Logit, right? If data is very condensed, not too much variation, regression is the best, right? So turn out if you learn machine learning as well later next week and onward, you'll notice that regression is usually most of the time is the best. I mean, if you do it rightly, machine learning will not gain a lot of stuff. Of course, if your system, a lot of variable, very complicated, probably you would probably need some machine learning method or complicated method to do what you want to do, right? But for the moment, this is fine. For small scale thing, okay? So how to measure goodness of fit? Of course, you can use R-square, but usually it's not the best, right? Because you can always calculate R-square, right? Something like that, but not a good idea. So the most commonly used is called, I think what we call is called the pseudo R-square, okay? Which is this guy, which is called the Manhattan R-square. It's 1 minus something. If you remember the R-square, we learned from the regression. It's like this, right? If you remember R-square, we learn is 1 minus SSE over SST. This is something we just showed you before the break, right? Because SST minus SSE SSR, right? So this is the part 1 minus the part that we didn't explain over the part we want to explain, right? So here it's somewhat similar, right? Because SST is what? When the model have intercept, right? Remember, SST is you constant regression only have the intercept. There's no X, right? And it's same here, okay? Here is you fit the model with intercept only, the null model. And this is the model that you try to fit, okay? I will talk about the this likelihood very soon, but there's a ratio. This is tell you the rubbish model. This is full model, the model you estimate. There's a measure. I'll tell you immediately what is likelihood first, okay? But that is the thing. But let's look at the likelihood. So likelihood is a technical slide because we didn't need that, but we'll just go to the technical slide first. So the question is like this. Okay. Now, maximum likelihood is a way to estimate things. Okay. And for example, I have this duster. Okay. I want to flow it. Okay. Likely you end up either this or this, right? Head or tail, right? So something in the middle, maybe not good example. Maybe I should have something head or tail. Okay, imagine I have a coin, imagine a coin, I throw it, it's head or tail, right? But I don't know the probability, right? So I don't estimate that, right? There's only one thing is P, right? So one is for head, tail is for value, I want a head, right? So the model will be, if you give me the probability P, right? That is the model I have, right? The thing is I want to estimate P, okay? And if you combine this, then this is the model, right? This is, if you learn the, from undergrad, this is called the binomial trial, okay? 伯努尼分布, right? 伯努尼分布. And the thing is, we want to find out the best P, right? That would get best guess, right? Suppose Y is 1, right? Then you would more likely the P is higher, right? If you keep having many toes, they're always 1, then basically P would be very close to 1, right? If you have many 0, then probably P will be goes to 0, okay? So note that this is, if I give you P, This is how we realize, right? If I told you what's the P, then what observed in the world will be following this probability function, right? So the question is, I reverse this. I have Y, which is the outcome I observed from the data. I try to find a P that maximize this guy, which is not probability, we call likelihood, because the idea that probability haven't happened, right? But something happens, so we can't say probability, we call likelihood. So we want to maximize this, right? We just reverse it, okay? So that's what we do. We try to find the best P that maximize this guy, we call likelihood, probability, right? So that is the likelihood means, okay? We try to basically adjust this parameter to make sure that this probability that is maximized. Okay? But we don't have time to go over this deep concept here. But here is what we have, right? We have observed y, x1, x2. The data is y is either 0 or 1, right? And the length function, right? The p will be, okay, is this gamma function. So you just try to, in the Python, you just try to put in this value there, right? And try to figure out what's beta 0, beta 1, beta 2, and also become what gamma you're doing, right? You estimate those, right? If normal, you're the mean and variance, right? And that would be the idea there, okay? So for short, likelihood is how fit the model is, right? If, for example, if model fit perfectly, right? Suppose P is 1, right? You always observe Y is 1, right? Then this actually likelihood would be 1, right? Because all Y's are 1, right? This is 0, the best fit is 1, right? So it should be the best fit for you if the likelihood will be 1, all right? And that would be likelihood, right? The better the fit, the higher the likelihood. So that means that I look at this, Manhattan R square. If your intercept, the fit is very poor, this will be, okay, a number that is, because log, so a number that is actually that will be bigger. Why? This is a math class, sorry. If your x, this is log of x, okay? 1 is here, 0 is here. High school math, what is the shape of this graph? Log cannot go to negative, so look like this. You recall? Right? Just go to 0. Log 1 is 0. Of course, you go up as well, but right, something like that. All right? So, as I said, the likelihood is smaller when it's less fit, right? So, we're likely that your model with intercept only will be somewhere here, right? So, this may be L0, and the height will be log L0, which is negative, right? And if model fit better, that actually is closer to 1, right? So maybe your model is like this. Your model is good fit, is somewhere here, L. Then you map to here, that will be log L, right? So the Manhattan R square is 1 minus log L over log L0. Okay, it's just comparison of these two numbers. Okay, 1 minus that.
Okay? So, of course, if your model fit very well, then become 0, then 1 minus 0 is 0, so R squared will be 0. If your model is so crappy that actually no improvement, that will become here, right? And then the same thing, right? So then the last guy is 1, so 1 minus 1 is 0. So this is what we call the method in R squared. Is that clear? Is that okay? So this is what we call the pseudo R square. Sometime. Okay, so the pseudo R square is here. Okay? 0 is useless, 1 is perfect fit, as I said. And the other one that we have seen, the likelihood is also a measure, right? How fit they are. So you don't have to over the L0, so this is also -2 of this is also a measure. Right? Why negative? Because we're negative, right? Then we want the bigger the worse, right? I get a math class, sorry. I'm sorry about the math because, so this is, let me another slide here, right? So this is L, right? Or X, if you want, X, right? Which L will be better, right? L, this is log of L, something like this happen, right? We've drawn it already, right? And if you do this log of L, if you draw the other one that is negative log L, will look like this, right? It's a mirror image, you flip it, right? This is simply the high school math. Right? Another high school math is if you multiply by 2, right? There's somewhere here, right? That will be -2 log L, right? Still, how fit the model is, so the much fitter, they will much closer. Why -2, I don't know, but this is how they define. Okay? So, I mean, I'm not defining this concept, it's just here. I just explained that why, look at this, when you compare model, look at deviant. Okay? And of course, deviant only apply for model when you estimate full maximum likelihood estimation. Okay, otherwise, it's not well defined. Now, let me go back to this one. So beside this, we have 2 more measures. I think that's the most crucial one. It's called AIC and BIC. Okay? And which you will use it for time series regression or many model that require to estimate under maximum likelihood estimation. Okay? Just a side note, you want regression, you can also do MLE, but usually we don't do that. But you can also do that as well. But anyway, you will see that AIC and BIC are very similar, right? The first part is deviant. The second part is slightly different. The first one is 2 times parameter P plus 1, we call complexity, which is number of parameter you estimate, right? So it means that if your model is better, the deviant will be smaller, right? But you increase your complexity, the first term reduce, right? Usually. But the second term will increase, right? So it's a trade-off, right? You should increase the parameter only if you reduce deviance sufficient enough. There's some trade-off. So it's an automatic adjustment, right? So just like the adjust R square, right? You increase K, you should reduce SSE good enough. Same idea here, if you increase parameter, you should reduce the deviant big enough to make it good. Okay? So the next one is very often also see as well, is called the BIC. And BIC is instead of 2, you use the sample size log of n because of the fact that if your model get more complicated, right, it's very tempting to use more parameter, which because it reduces this deviant a lot, right? So that's why you would actually make more punishment on that, okay? But usually they give very similar answer anyway, so it's not a big concern. But you would often see BIC, AIC as your model, as to compare the complexity of your model. Okay? And there are other two more. Sorry for that. Okay? The first one, B.B.A score, is actually MSE, but in the context of Logit, right? Because it's what you estimate minus the data square. Some of them the other end is MSE, right? Just to make sure, this is just MSE. All right, this is MSE. MSE. Right? It's not probability, that's an MSE thing. Nothing very deep there. Okay? But of course, why I want to do that, because we should do something like this crazy thing. Okay? Log loss. I don't want to explain, but it is some crazy format. Okay? And it's useful when later you do machine learning, there's some log loss is also comparable. But I don't want to dig too much into this one, but there's some function there in the Python you can apply. Okay? But I'm not going to go over that. But that is something that we can do. Okay? So this is the Python code that how we do the B.B.A score, but that is actually SSE, so I'm not going to repeat that, the same SSE. You look at prediction, take the difference between y and y, predict sum or square, and then look at the mean. I mean, we do that for SSE already, right? So the same code there. But now what I want to show is this important table, right? Probably that's the most important thing is you want to look at which model to fit, right? So I have LPM, Logit, and Probit, right? And look at R square, you can calculate R square as well, right? Because it's the definition, right? Because 1 minus SSE over SST, right? You can always do that. And this score make not much different. And pseudo R square only defined for Logit and Probit. As I said, Logit and Probit very similar, the same thing. Only the log loss is also very similar, right? So that's why you can see in general that usually there's not too much different, right? But we still mention it because of we use some of them when we talk about machine learning method. Okay, and when you later learn classification, this is something that you learn. We don't talk about, probably don't have time to talk about this class, but when you learn machine learning, then they assume you learn Logit and Probit. So I have to talk about something. Otherwise, people will blame me. Okay, I'm not teaching Probit Logit. Then you have some concern when you learn machine learning. But I just very quickly brush over to make sure I cover something already, right? So you can't say I didn't cover anything. I have something already. And you know how to run the regression, right? So you have that already, okay? And it's important, right? Because of many of the time you want to care about whether some guy kicked your website, it's 0 1. Whether they buy your stuff, it's 0 1, right? And the problem probably sometimes is you don't have further measure, right? Or the variable y, probably the better is like, it's not whether they buy your product, it's how much they spend. But sometimes you don't have the data. You only have access to yes or no. Then you have to use this kind of model to model that, of course. Just like the healthy, right? Where they think you're healthy, it'd be good if you have a machine that can tell you are healthy with score number 10. No, you can't, right? So that is the thing. Okay. So I'm not going to talk about the calibration. This calibration curve is exactly the y hat idea, right? But flip it a little bit, right? This is the predicted and actual, but you just flip this guy, the same thing, right? But what we want is, we want it to on the 45-degree line, right? And the way they plot is not plot all the number. You look at this plot, they look at 10 bins, Okay? So what they do is, you have data, you spread it into 10 different groups, right? And you can look at the group, look at the average success, and the model predict, and you plot this graph, right? So just, do you get what I'm saying? Because you can also, so you can, okay, maybe just, so the graph will be like this, right? If you remember the YY head plot, right, is we plot 45-degree line, then there's a there, right? Remember the hotel thing? Okay? You can also do the same, right? Looking at the, but you cannot do individual. Why? Because individual is just 0 or 1, right? So plotting this will not be very meaningful, right? So that's why what they do is, because the data, what we have now is like this, right? If you recall, the data is like this. Sorry. The data is, you have X and Y. Your data is just bunch of 1 and bunch of 0. Right, something like that will happen, right? That's your data, right? So you can't really plot this kind of graph, will not be very too meaningful because only 0 or 1, right? So that's why, because the data Y is just only 0 or 1, right? So basically you just bunch of 1 here, right? So that's why they group them, right? Group data into 10 different groups, and then in different groups there will be some success, some fail. Then you can plot something like that. So that is called the calibration curve. The same idea, you just group them there. The code is very simple. So did I write it down? Did I do it? Yes, I did do it. So what actually you do, so what I do is I'm not going to go into detail, but just basically I generate data. I cut them into 10 different bins. Then I look at the bins, then look at the mean, and then I plot this guy, okay? Because I don't think you actually need that graph, but I just want to show you that this is one way to calibrate. To be honest, I never use this graph in my work. So that's why, yeah, because the same as the Y hat, Y plot. Okay? You only use it when you really using this, the model in practice, and you look at what is not so good, and otherwise I don't really care. Okay? So that's why I will brush around. Okay? Sorry for brushing over very quickly. As I said, this is not the crucial chapter. I think I'm not asking assignment question on it, and also I'm not asking, probably, I'm not sure whether I will ask question in the final test, but probably not. In case I do, I will let you know, but likely I'm not doing tests on this one. But I just want to know there are ways that to modify the regression to handle 0-1. Okay, and you're using it in the machine learning class as well. So that's why I want to put it there. For those who don't know machine learning, probably this is not very useful. But because linear model would work most of the time, right? Because remember the example we have, right? Most of the time, when you talk about fit, right? In this case, the method you use actually is not that bad. You don't see much problem there, right? You use it when you really go to more deeper thing. Okay? And final remark before we get a break, it will be, okay, for some of you who are not doing data science or doing ITM, right? I see some of you looking for jobs not in this area, right? Then what's the use of my class, right? At least you know how to look at data, right? Even you want to record a TikTok, right? Want to record a video, or write a letter, right? And then you can tell people how you analyze the situation using data, because data can tell you a lot, right? Rather than using our heuristic thinking, right? There's data to support what we are saying, right? Suppose at least you can say whether smoking is healthy or not. At least there's some data you can run to tell us something, right? At least when you try to record a video, try to tell some people a story, at least you can say something, right? At least based on data, you can tell us rather than impression, because impression usually is wrong, at least data can, even simple data can tell us a lot. Right? I hope, try to help you on this one. But anyway, again, that's a break of 15 minutes, and then we will resume at 11:35. Okay. And as I said, I will skip the time series regression. So the break will immediately go to lesson 7. So we'll talk about prediction. Then we'll be in time to do LISO, which is the first machine learning model, next week. So we will do the prediction today. So we will do machine learning next week. Okay. So let's have a break of 15 minutes, and then we will see you again soon. So let's go to the U reply again, and then I will do the if you have time, please do the U reply, and so that I know what you don't know. Okay. So if you have something confused or what, let me know. Just ask the question. I try to answer them.
Hi. Welcome back. So we come to the very last section of today. After that, happy Friday and happy weekend. And unfortunately, next Friday is November 1st. It's not October 31st. Otherwise, we can have a Halloween party in the class. But okay, if you do, you can. I mean, we can have a Halloween party. We can dress up, have fun. But but we don't. But I enjoy the other class on Thursday. So no, okay, that's fine. So the only comment I got is sleepy. Yes. So that's why I got my coffee, because I also feel sleepy, so I have some coffee. Also, one thing that one tips of staying awake in the class, which I do in the US, is to buy a chewing gum, which is very useful. Usually I would have one chewing gum per section of the class. And in US is chewing gum is very cheap, so I keep eating chewing gum. And when I get to Singapore, there's a problem, because you can't eat chewing gum, right? Because Singapore, they ban chewing gum. So then I have is coffee. So that's how I pick up my coffee, because I don't drink coffee when I was in US. Although many people drink coffee there, but chewing gum is the best, because you keep your mouth keep moving. And that's why in my office, if you ever come, will be full of snacks, because when I feel tired, I just eat. So hopefully you can stay awake. Now, as I said, we're done with this lesson 6, so we go to lesson 7. Okay. So here we get some more real business of prediction. Okay. And then we don't have time to cover LISO today, but we'll do LISO next class. But what we will do is do prediction, okay? And by prediction, what we do is basically horse racing, okay? It's horse racing. We have different type of model. We try to compare them and pick the best one. And there are ways to evaluate how they're good or bad, okay? But we will go to very soon how to do them, okay? So just matter of terminology, because this is what the book would do, is we call Y is our target variable when we do prediction. And that sometimes they call dependent response of outcome. And X is called features, or sometimes they call variable or independent variable. And features the language that people machine learning you use, so that if you do machine learning class next semester, that's what they call. And the idea is use X to predict Y, okay? You don't really care about whether you're star in the regression, whether R square is good or not, but you want to care about the fit of the model. But it's goal-oriented. You don't care about how to get to the answer, but you care about whether your answer is good or bad. Right? You don't really care about the mean to there, but you care about the ends. Right? The end justify the mean. Okay? And of course, we will care about the means with the very last 2 classes when we talk about causal analysis. That would be we care about whether marginal effect, right, is meaningful and makes sense. Right? That would be something we care about. But here, you just care about the end. Okay? And here, it's very important, we have 2 distinctions. Is what we call original data and live data. And original data is something we use to build a model. Sometimes we call the trained data. Okay? And the live data is called the text data. Usually it's the thing that we use to test our model, how well it's going. But it will be clear very soon, so don't worry about that part. So it's X and Y and train. And I think we have, in the textbook, they have 3 different motivations.
And we'll focus on the first one, okay? Where if you want to sell a car, you have second-hand car, how much on the sale? You want to put an ad on a website, and then how much on the sale, right? That is the easiest question, right? Then how you want to do, right? What is to be the market price, right? In the market like this, what you want to put on the ad, right? So that will be the question. And how you want to solve it by data is looking at current in the market, right? At what feature of the car, at what price being sold, right? In the data, and can tell us how you would set the price for your car, right? Because different car, different feature, right? If every car the same, then it's very simple, right? Just what is the price is now, then you can sell it, right? But what happens if different car, different feature, and how can you do it based on data? Okay? That's what we want to do. So the prediction have many types. We have said, right? If y is continuous, then you can use regression, right? If 0, 1, then probably you have to use Probit or Logit, right? And the last one, I think, is we will learn a lot in machine learning next semester, not my class. We call classification. It's a one step ahead from probability to this one, right? The probability is just, the model we estimate is how likely that is 1 or 0. It doesn't give the final answer. If we get one more step, you just tell me 1 or 0. Okay? How you can jump from here to here? Just one more step. Say, you set the threshold, which should be estimated optimally, is if the probability is more than, say, half, you will say 1. If less than half, you say 0. But can be, half is not necessary, can be 0.8 or can be 0.7. Then you can decide which is the best. Okay? And that would be classification. And that is a machine learning model, which we don't study in my class, but some other class will focus on how to do that classification. Okay? And we just focus on the first two. Okay? I talk about that because this is what the book is. And we want to look at prediction. We have seen many times is how to look at the prediction is look at how good your fit, right? The difference between what you predict and what's actual is called the error, okay? And this is the key, and look at all the machine learning textbook. They will tell you the first chapter, always they tell you the decomposition of the E, okay? There's always, you can decompose it into 3 different parts, okay? The first part is for bias, okay? Which is because coming from the fact that you use the wrong model, okay? And you overfit because you fitting the model based on the feature only in the trained data, not the real data, right? Some data may have some problem, then there's a bias, okay? And later you will see how we correct them. And the second is model. You use the wrong model, then you make it wrong. Say suppose you don't use the square term, it's nonlinear, right? If you use the square term, you improve, right? We did the first model in our class today, right? You fit the distance, you take the square, then R square actually better, right? And the last one is genuine error. That means that this error, you can't really do anything about it because the nature is random, right? In some sense, you can't really avoid. So this is something we cannot do anything. This can be done by better model. This can be done by not overfit, underfit. We will talk about underfit, overfit later, very soon, but that will be the idea. Okay? And you look at any textbook, they will tell you that, at least in the introductory, how you look at the error, the loss function, is by looking at the square. It's not the absolute value, but square is because of they're symmetric. The green one is symmetric, right? The purple one is not symmetric. And this is linear. You want the convex. Why convex? Because the further away, the larger the error, you want to punish more. You want to square, right? But probably the question is, why I don't go to 4, right? Or 6? Yeah, but square is easier. I mean, there's some reason why you square, but that is the way to look at. And
I hope you remember the MSE, right, this guy. And if you remember when you talk about regression, I minus K as well. But when you compare across different model, the MSE we use is this guy. So we don't minus the number predictor. Okay, it's just this one. Okay, MSE apply to any kind of regression you're thinking, right? Any type of model, you can do MSE, right? No matter you do this or that, whatever, MSE is always well defined. Okay, and because MSE can be very large, okay, so very often we always usually compare the root mean square RMSE because the number is much smaller, right? You take a square root, the number is smaller, but there's no difference between the two. Right? The comparison is same when you do root mean square or mean square error. Okay? The same thing. Okay? You will notice the horse racing we do is very often is this guy. Okay? Or the MSE. The horse racing, usually we base on the MSE criteria. Of course, you can use other criteria, but MSE is the easiest one. And we'll use this for our horse racing exercise. Okay? This is the technical slide that I skipped. Okay, so let's look at the example here. Okay, as we said, we want to look at the car, what car to be sold. So I look at the data from the website and decide what car to be there. Okay, and say what should be the price, what the location is, and whether the car is good or bad, and what the type of the car you are. And whether the post is by dealer or not dealer, because in effect, whatever dealer have some margin they add, right, because they sell, you have to give him some profit, right? But anyway, this will be the variable, okay? And to clean the data turned out to be a very difficult thing. I mean, you have to clean a lot of things. First, because they collect the data contain many areas, they want to filter the area, focus on Chicago, because you imagine you're selling in Chicago. And you have to figure out that because lack of observation of data, then you drop when the car is new or fair condition, just keep something good. So new, you don't want that. Fair means very bad. You don't really want that because few observation, so you take something in the middle. Excellent, good, light new, something like that, okay? And also you don't want truck, okay? And you only want the auto, not the manual, right? How to the car. And if price too low, then you also want to cut it because maybe they're fake advertising. Okay, so that's what we do in the slide. Okay, so what we do is download this data. Okay, we work on it together and see how we do horse racing. Okay, so let me do quickly because I think we don't want to run out of time. So this is the data we download, okay? Again, once we download, then probably you want to look at data, how it looks like, right? Because that would be the first thing to do, okay? Download data, right? You can see what's the price, what's the area, sub-area, what's the name and condition, right? Good, excellent, and how many cylinders you have, so on and so forth, right? But the price here, when you sell it, right? When it's available, right? There's many data, you can see the second-hand price data. And the second thing is a little bit more complicated, is there's missing there, okay? So what we do is, there's a NA there. We want to fill the NA by missing, okay? So if the NA, we call it missing, okay? That is what we try to do first. So we place any NA, we'll call it missing. Right, that's what we've done. We fill everything by missing. Okay. The next step, as we said, we want to focus on Chicago. Okay. We want to focus on the case only new and fair because you can look at condition, you can look at the value count. Maybe I just do it to make sure that you know what's going on. So you see, you may ask,
here I use another new type of notation here. I use the DOTE. This is also a way that different from Python to, I think Python are allowed that, but they allow that you can use the square and double dot there. If your variable name don't have space, you can use this dot notation. Okay. So I can say, for example, I can do this. df dot type, right? It's a type. Okay. Condition. Condition dot value counts. Okay. This is same as you run this, the same thing. The dot is same as you can do this. And probably ask me why I do that, because this is the code used by publisher. They also do that as well. So I just show you there's another way to do it. The same thing. You can use this column thing or use the dot. Okay. As long as your variable name don't have space, the same thing. Okay. When you have space, you can't really use the dot because they can't really handle the space. If the name of the column has space, you can't do that. But you can see, now you can see the reason why they don't like new and fair, because only 19 observations you want to drop this, right? So that's why we have here, right? We're going to focus on that. And most of the car, auto car, this at the data. So not many manual car, okay? So that's why they do that. And then to drop the truck, so I think just copy and paste here. Just run this. So is that okay? We can check how many data we have right now. Once we run that, we still remain at 300 something data point. Okay, after the filtering. Is that okay? I just stop for 10 seconds to make sure that you're okay with that. But in a question, let me know, because I want we do it together, right? That would be helpful for learn, because right? Because now everything can be done online easily. You can AI, you can ask them, but I want you to run with me, then you know how to handle it by yourself, right? Because okay? Probably okay, any question? If no, then we can continue, because if you don't like to run it, you can run it at home, okay? The next is you have to reduce some unrealistic price, right? For example, the odometer, which means how long they drive the car, is too low, and then the price is too crazy, right? Then you probably don't want to keep it there. And same for the age, the price is too low for young car, then you just drop, okay? Just you drop something that is crazy, okay? And remember why we do that. If you remember the first class we learned, garbage in, garbage out. So that means that we really need to do something to clean up things, right? So this is how we clean the data, okay? If you don't clean it, it's okay, okay? Here is what we want is to create what we call dummy variable, because the condition excellent, good, or naive are not number, okay? We create dummy variable, right? If this is yes, it's 1, otherwise 0. Okay? Is that clear what we're doing? Okay? Because the data you have, look at here, right? The conditions are just word, right? So you really want to use it, right? You create 3 variable there. I want to see that this will change, right? So that's how we do it.
Okay, so that is what we're doing. We clean up the data and define new variable, okay, such that if according to condition, I have the dummy variable. Okay, so this way often we use it. Okay, and the next is for cylinder, right? Because cylinder is either 4 or 6, right? So I just need one dummy. Okay. So I just need this line, but I can also do this thing to see what it looks like. But I just need this one because I just need cylinder is 0, 1. Okay. This is the part I need for my code. Because so this is the thing we need, right? Then of course you can check, you can do the value count and check what it looks like there, right? And see only 42 of them are 6-cylinder, the other one are just normal, right? 6-cylinder, the car run faster. Okay, I don't know about cars, but this is what it is, right? I never drive, so I don't know. You guys may drive, you know, because I have no idea about cars at all. Now, let us create variable. You want square term, right? It's h square and a cubic, right? And then I also want the odometer, which how far you have drive the car, is also there. Okay, we have 3 more terms. Okay, then we are ready to run the regression. So basically clean the model, clean the data, create new variable, drop some observation. So these are very standard way you do it, right? You expect to do the same in your assignment too, and also in your project as well. So basically I involve you from the beginning of the data to the end of the process. Okay? So there's nothing left, no undone, right? So we leave no stone unturned, so everything is done. Now we are ready to run the regression, and according to the book, there are actually 5 different models. The first one is this using age, okay? The second one is age and also how much you drive, odometer. And the third one is looking at, in addition, you have some type of the car condition and whether the dealer, right, and another type of model, right? And everything in age interaction, okay? So you see that is something like crazy thing, but you can see that's how they do the thing, right? It's nothing new there. Just model 1 is this equation, model 2 is this equation, and so on and so forth. Is that okay? So just copy that part, okay? Nothing new here, right? Just write down what the y, what the x is, right? And just copy. Okay. So I hope it's clear there's a model, and then we start running the regression. Is that okay? So I have 5 models. Of course, you can adjust as you want. Okay. This is something that you will do it in the assignment as well. Okay. So you have to write a complicated model. So why I want to create a list? You ask. Because we are programmer, we want to do a loop because we want to make our code easier. We write a list and loop over them. Okay. So what we're going to do is I run this formula, I put the regression, the list, I use a for loop over its equation, I run the regression, you can use 1 or 3 the covariance, I regress the equation based on data, I append it, so that means that I would put it there. Is that clear what I'm doing? Is that okay? The for loop, I guess, shouldn't be too complicated. Okay? Because I want to run everything line by line, right? So I just do it, okay? And as I said, I want actually 3 because it's better, okay? And remember there's a space, okay, for that, okay? So this run, and what it means is this regress will contain all the regression results, right? With 5 equations. That means that you run 10 equations, they will run. So actually that's the why using Python is good when you have a large complicated model, right? Because when you run data, then you have to run many, many lines, and Python can do it quickly, okay? And R is also okay, but I think Python in that sense is easier in terms of writing the loop and thing, because that is designed for that purpose. So that's why when you do machine learning, horse racing, that is easier. Okay. Is that okay? Is that okay what we're doing? Now, once we do that, we do star glazer, which will give us the model result. It's just printing everything out. Okay. Okay, we will just do that. I don't think we just I think we don't need that. Let's see. We just install this. Remember, if you want to use it, if you have in your own system, you can just install that. That's no problem. Okay. And so I use the star glazer here and take out all the results. You can see I have a 5 regression, right? They tell you everything there. There's first regression based on age. The second one is age plus odometer, right? And square and so on and so forth, right? So these are all the things that I need, right? So you can see that some have star, some have no star, then you can decide what to do, okay? But when your prediction, you don't really care about the star, okay? If you try to use it there, because the goal is prediction, so this is not the thing we care. The thing you care probably is here. The thing you care is R square, R adjust square, and the residual error, okay? The thing probably we want to look at R square first, right? Of course, R square must be increasing. But the adjust R square is also increasing as well, which is very comforting, right? And the thing is this big enough jump? I don't know. You have to make your own decision, okay? But if it's based on R square, that's what we have, okay? And adjust R square, okay? But at least this is the first round approach, okay? At least adjust R square is not decreasing, okay? So model 5 still meaningful, okay? So not that bad, okay? But we will do the horse racing in a much better way. So this is the first thing we have, okay? Is that okay? I think there's nothing new here. Now the new thing is we have the table here, okay? And you can do prediction, okay? Based on your model, okay? Suppose the question is, if I have the car, age 10 years old, the meter is 12 and all this thing, and then what's the prediction, okay? And the prediction with 95% interval will be like this, okay? The mean will tell us this is the price I want to set my car, and they are the interval, okay? And so I don't know which one you like, but at least that the first one is too big, the range, not very good, right? And the one as you get more complicated, the actually shrink a little bit, right? And you can create this by little bit complicated code. You input the data, you code the panda data frame, and you input new data, you have to put data series, and you have to tell me what are they using a dictionary form. I'm not going to detail here. And dictionary you have to do the DOTE because I have to transpose. I'll take the column. but I'm not going to go into detail on that one. And then you plug in this observation and gap prediction and set 95%, and then this will give you this table. Okay, I'm not going to go in detail in this one. What I want, because you know already that one, you can have fun at home if you want, but I want to spend time on the following, is the horse racing part. Okay, and how to do horse racing here is, you will see, we'll show you soon, is if you use all your data, what you have to estimate, the more complex a model you estimate, the root mean square error always decrease. Right? Because as I said, the more complicated the model usually get better. But the problem is you go to the live data, you go to the real world to apply, turn out to be is not the most complicated nor the less complicated best. It's the middle one. It's like what we learn, 中庸, right? Somewhere in the middle, right? Somewhere in the middle is the best. Then we have to find the best one. How can we do that, right? How can we mimic the idea that when things put in production, how to look at this problem? Okay, we will call what we call cross validation. We call validation method. Okay, but before we do that, actually we have something that there is called adjust R square, AIC and BIC that punish the complexity, right? If you're more complex model, it not goes down, right? So that is the one way to do it. And the second method that we will use, and actually is the one that used in all the machine learning approach, the most common one, is called, we divide the data into two parts, training set and data set. Okay? And then say, for example, we have 100 data points. We use 80 data points to fit our model, and 20% data point we will test it. And that will be the comparison goals, right? So 80%, we fit 5 different models. Okay, once we did that, the remaining 20% will be used to horse racing. Is that clear? Because that will be the easiest. Okay, that's called validation, which we will show you very soon, very quickly. The other one is called, it's slightly more complicated, it's called k-fold cross validation. Okay, which is best explained by a graph. Let me explain by a graph. It's like this. Don't worry, this part if will be Python can do automatically for you. So what's going on is this is data, right? So you would do is the first one is you keep the first 80% to fit your model, right? And the red one, you calculate the MSE, right, or root mean MSE. Then you calculate for all the model. So you have MSE 1, right, is the model 1, right, you have 1 here. Model 2, you have 2 here, model K here, right? In the case I have 5 model, and I will do this once, right? But this is only one way you cut the data. You have second way to cut the data. You do the same, okay? And you do it 5 times, okay? And average of all 5 scenarios give you the MSE1, MS2, MSE5, and we horse racing based on this. Okay? Is that clear what we're doing? So don't worry, Python will do it automatically. We just need to input the code that we're done. Okay? But this is how we do the horse racing. I don't have time today to go over the code, but look at the result first before we go to the code. So at the end of the day, as you will see, maybe the graph will be better. Oh, I don't have a graph for me. Where's my graph? I don't have a graph. But anyway, what we have is the root mean square error, right? If you increase the complexity, this actually goes down, right? This number goes down, but at the end goes up, right? So adjust R squared tell you pick the number 5, right? Because R5 is best. But if you use this horse racing method, you would pick model 3 or 2 or 3. Sorry, model 4, 3 or 4, right? Or maybe I'll pick 4, right? 5 is really high. Is that okay? So because just R squared only tell you how it fits within the model, right? When you put in data that is not explored, then you don't know. Is that okay what we're doing? Now, we quickly go back to do the validation method first. And if you have time, we can do cross-validation as well. But so how do we do validation method? Okay. We will use what we call the tools evaluation measure input RMSE that will calculate the RMSE measure. So that is the function that gives us RMSE. Okay. So what I'm doing is I will do a loop. Okay. I will set initial list as nothing. Okay. Validation. This will be this something I put in there. Okay. What I'm going to do is I look at a loop. Okay. That is, I use the counter, the equation, look at enumerate the equation. This is the way to do the for loop in Python. That is the most Python way to do it. Okay? And what I do is, for each equation, I look at this snail, and this is my y, right? Because the equation is a string. Basically, this is a price anyway. Y is a price, right? And I run the regression using the data, okay? You can change it to covariance to make it, but it doesn't really matter because where covariance doesn't affect our prediction. So we don't want to bother with that because the prediction doesn't affect the coefficient variation. So that's why we skip that part. That's fine. And number of coefficient will be look at the degree of freedom model plus 1. That is, and RMSE will be looking at what the model predict against the data you have. Right, that's not the y, right? The data, the y. Okay, and you can calculate, estimate the model, the BIC and AIC. Okay, do the loop thing. And you want to output RMSE, the data, right? This become the validation method. Okay, and this will give you this guy. Okay, and okay, and here, maybe that says, I think I have to. I didn't do. I mean, I should do it next time because this part I should not do DF. I should first divide the data in 2 parts first, 80%, 20%. And then run there, and when I predict, I should use the other new one. I'm sorry, I mean, I should change the code a little bit. So this one I should change to the train data. This will be test data, and then I should do that. I'm sorry about that. I mean, I will update the code later. But you should compare, this is called the validation. You should cut the data first. I'm sorry about that. And cost validation is very similar. I will cover that next time, but involve we call sklearn, is the learning machine learning package with a k-fold. Okay, I just very briefly here, but I will talk about that next class as well. Then very similar here. Okay, and then what I do is I would separate the train data and test data, and run this every time. Okay. And then I will combine the data. This is what I have, okay? And I would change the code later. So there's some typo in the validation code, okay? But that's how we do horse racing, okay? Sorry for the wrong code, but that's what we have, okay? So don't worry about the validation part because I'll update the code. I'll talk about that again. So I guess we learned the horse racing, why it's important because this session of classes, we learn do prediction. The important part is horse racing, right? Because you want to see which model fit the best. And the horse racing criteria is RMSE or MSE, right? And then just by looking at the overfit RMSE is not good enough. What you want is you want to do the validation method, right? So you keep 20% data, and that is the horse racing part. Okay? And you also want to do the K-fold validation, right? Cross validation, that will be something like, which we set the graph like this, which we'll talk about this in more detail in the slides next time, because I think I just update it. I mean, there's some typo there, but I'll update that. Okay? Is that okay? So, if no question, just then we will then let our class end here. So, but in case you haven't done the Google Sheet, please do it when you have time. We have B.B.A boy already, so I don't know what B.B.A boy is, but have fun. Okay, I will see you next month. Enjoy your Halloween. Okay, you should try. I mean, especially if you try the Ocean Park, the Halloween haunted house is fun. You can try that thing. Okay, see you next week, next month.